So it is my pleasure to present Freeke van der Voort. She is an expert on cosmological hydrodynamical simulations of galaxy formation and evolution. So she did she was a grad student at Leiden University, where she worked with Yox K. Her thesis dealt with the growth of galaxies and their gaseous halos. After that, she did a couple of, well, a few joint postdoc positions, many places. So she was first a TAC and Asia Fellow at, with a joint position at UC Berkeley and Asia in Taiwan. Following this, she was a CHIRA Fellow with a joint position at the Heidelberg Institute for Technical Studies and also at Yale. Since March 2020, she's a Royal Society University Research Fellow and a lecturer at Cardiff University. In today's talk, she's going to tell us about cosmic gas flows. So thank you, Freeke. Please go ahead.
Yeah, thank you, Sundar. It's great to be here for my first online talk. So I hope, well, I hope it goes well, and I hope that you enjoy it. So yeah, indeed, I will talk about cosmic gas flows and how they relate to galaxies. And let's get, oh, okay, sorry. But first, I want to tell you why this is such a fascinating topic to me, and then hopefully you'll understand and agree. So galaxy formation connects to many other topics in astronomy, because galaxies form in the densest regions of the universe, and therefore they trace out cosmic structure. I'll come back to this also in later slides, but also, so they connect both to these large scales around them, as well as to much smaller scales, because they are also affected by the stars that form inside the galaxies that explode as supernovae. The supermassive black hole can produce jets and push matter and out into their surroundings, and therefore galaxies aren't just affected by large-scale structure, but they also change the environments that they live in. So in that sense, this connects to many other topics, and well, we of course don't really treat all of them equally accurately, but at least we need to be aware, and we need to make our models so that we're capturing the sort of larger scale effects of the smaller scale physics that we can't really resolve. So how do we set up our simulations? So for those of you not working with these types of cosmological simulations, what we do is we take the power spectrum, the fluctuations from the observed cosmic microwave background. That then sets the initial conditions. So in a sense, there's no freedom there. The initial conditions are much easier to set up than for other numerical problems in astronomy. And then we let it evolve. So we put in the necessary physics, or at least the physics we think is necessary. And then mostly under the influence of gravity, matter collapses into the sort of large-scale structure of the cosmic web we see in the present day. And for that, I have a movie. So here you can see the very boring, very high redshift universe. This movie starts at redshift 20 or so. And this is a movie of the gas density. So the blue is low density and red is high density. And it was pretty homogeneous early on, but now you can see that, again, under the influence of gravity, everything is collapsing. So first, it collapses in one dimension, preferably. You get these pancakes, then you get these filaments of the cosmic web, so these red lines and filaments you can see. And then in the centers of where these filaments intersect, you sort of see this three-dimensional orange structure appear. And this is where the most massive halos live. And in the centers of these halos is where you get the most massive galaxies. So again, here in the light blue, you have the voids, and in the yellow centers, like the central pixel, you can barely see it. That's where the massive galaxies live. So I want to just make sure that we understand what kind of processes I'm talking about when I talk about galaxy formation. So here is an example galaxy that I probably just found by Googling this galaxy. This is an observation, but now I'm going to give it my theory spin. So in order for this galaxy to grow, gas has to, well, it has to accumulate material. So it can either accrete stars from other galaxies, or it can accrete gas from its surroundings. So this inflow, when I say inflow, I mean gas inflow. So from their halo or their circumgalactic medium is also what we call it. So from this gas, it can then form stars and thus growing. These stars, however, don't just sit there passively. They create outflows, for example, through supernovae. And so does the supermassive black hole that sits in the center. It can also create these strong outflows. I mean, this is observed. We don't fully theoretically understand it, but on the scales that I study, we care mostly about the sort of macro large scale effects of these outflows. So we put in very basic models and we get out our outflows, and then we study how the galaxy formation proceeds. So importantly, these inflows and outflows aren't completely independent, because outflows, they can bump into the gas that is flowing in, and they can also just not be fast enough or slow down so much by interacting with the rest of the gas around it that it actually falls back into the galaxy. And this we sometimes refer to as recycling. And again, these galaxies do not live in isolation, so the galaxy can also grow by accreting gas and stars from a companion, from a satellite. But the satellite can also, in its trajectory through the halo of the galaxy, get stripped and actually lose its stars and gas to the halo around the galaxy. So these are the processes that are, well, there's many more important in galaxy formation, but these are sort of the basic ones. And I will now show you results from simulations. So these are simulations that are relatively old, but they illustrate the effective feedback really nicely. So this is actually high redshift, or redshift 2. I guess it depends on who you are, whether you find that high. But it's a halo of about 10 to the 12 solar masses, which is the same as the Milky Way, but of course a lot longer ago. So this is one of the more massive galaxies in the simulation at this point. And here I'm showing you the density on top and the temperature on the bottom. And what you can see is that indeed this massive galaxy lives up. So again, the galaxy you cannot really see because it's really sort of the central pixel, and I'm showing you the gas properties. But what you can see is that this halo is fed by these more dense and cooler filaments. The galaxy sits at the center, and then if you look at the bottom panel, you can see that there's a hot halo that formed around the galaxy. So in this case, there is no feedback from either supernovae or from active galactic nuclei. So the vast majority of this hot gas is made by an accretion shock. So as the gas collides with the halo, it shock heats, loses kinetic energy, and gains thermal energy. So this is what it looks like, sort of it's not quite gravity only, but let's just assume that it is for now, for simplicity. So then when we add feedback, so now this is a model that models explosions from supernovae, you can see that if you look at the gas density, you can see that it looks more disturbed. So overall, it looks fairly similar. Maybe the density is actually quite, like, somewhat enhanced in the outskirts. But you can definitely see that the gas is much more disturbed because now there's feedback going off, not just in the central galaxy, but also in the satellites. And what you can also see is that the hot gas is more extended. This is both by adding more energy to it from these feedback effects, but also by having stronger outflows, which can push the hot gas to beyond the shock that it would have had without any feedback. And now to make the feedback even stronger, we've rerun the same simulation but added AGN feedback. So now the supermassive black hole puts in a lot of energy, and then this model is actually probably slightly too much, but that's okay. For illustrative purposes, I can still use it and show you that now the gas looks even more disturbed, and the gaseous halos also actually have very different properties. So the density on average is lower and the temperature is much higher. So we hope, so obviously these, because the galaxies are fed by the medium around them, this will also lead to different galaxies. And if we want to understand how galaxies form, we need to understand this phase, the circumgalactic medium. And also if we want to use simulations to make predictions for observations of this phase, we need to actually make sure that we make a realistic theoretical model. So that's what, I guess what my slide here is saying. Don't pay too much attention to the figures here. I just wanted to make sure that I said that we use these simulations not just because they result in nice pictures, but they can actually help interpret observational data. So especially if you're talking about the circumgalactic medium, the CGM, it's very faint, very diffuse, it's very low density. So often observations are, either just barely able to detect something, or alternatively, it's single sight lines because people look at a background quasar that probes that goes through the CGM of a different galaxy and therefore probes that its properties. So it can be very difficult to give this a good physical interpretation, and cosmological simulations can really help with this. And then we also need these observations in order to be able to rule out, if we have an observation of the temperature of the hot gas around the galaxy, we can, for example, if we know that it's 10 to the 6 Kelvin, we can rule out this model with AGN because now the hot gas is hotter than that. Like, this is just an example, and I just wanted to make sure that I mentioned like how it actually connects to the galaxies, and that it can be that these simulations both need to be verified or falsified by observations, and that observations can benefit from the interpretation allowed by our simulations. So these are actually type of the simulations that I work with now. This is again the gas density, but this simulation will run all the way to redshift 0 and focuses mainly on one Milky Way mass galaxy. So it's a zoom in high resolution simulation. So now it fades into the stellar light from the gas density. And you can see that these simulations have to cover a huge dynamic range. So we want the low density intergalactic medium as well as the high density interstellar medium. We want to form these nice stars. This is now fading into metallicity. You can see that the metallicity is highest inside the galaxy and that there's some low metallicity gas secreting onto this galaxy. So how we normally do this in cosmological simulations is that we keep the mass resolution of each individual resolution element fixed. So this is now the magnetic field structure. And then if you do that, then you get the highest, you get the best resolution inside the galaxy, but that means that the stuff outside the galaxy is not very well resolved. So I will come back to this and quantify it, but basically what you've seen already is that the CGM is multi-phase. So you have these slightly higher density, cooler gas phase, as well as a hot and low density phase. So in order to study this, what you can do if you don't want to have these sort of, in a way, low resolution cosmological simulations is you can put a cold cloud in a wind tunnel. So this is set up as a turbulent cloud in facing a hot wind coming from the left here, and then you can focus all of your resolution just on this single cloud and the wind that it experiences and see what happens. So what happens is that the cloud gets pushed and the clouds gets disrupted. But interestingly, so these simulations have about a parsec resolution, whereas our cosmological simulations have about a kiloparsec resolution. So we're really talking about 3 orders of magnitude better resolution than is possible in a cosmological context. But of course, you don't have the realistic initial conditions that we have in our setup. But what you can see is that as you go to higher and higher resolution, the properties of this super high resolution cloud change. So firstly, the bottom panel is the highest resolution, and this cloud gets accelerated less by the hot gas, and also it fragments into more and more tiny pieces. So this means that if we have a situation with densities and temperatures similar to this setup on a cosmological scale, then we have no hope of ever resolving it if it's not even resolved in these highly idealized simulations. So what to do? the standard approach, as I said before, but the movie was running, so I'm not certain anyone listened to me, is this blue simulation. So we have the best resolution inside the galaxy. So this is at 0 kiloparsec on the x-axis here. And then as you go out to the virial radius is about 220 kiloparsec, or even beyond to 400 parsec. The cell size of the simulation keeps increasing. So at some point we have cell sizes of 5 kiloparsec, which is orders of magnitude worse than in the center of the galaxy. And one thing that we have now done is add extra level of refinement. So these simulations in the standard way only have a fixed mass resolution. So you set up your simulation, you say you want it to be to have cells that contain a mass of, I don't know, 5 times 10 to the 4 solar masses. That's kind of standard. And then as you go to lower density, the mass stays the same, so necessarily the cell size gets larger. But now we have the same mass resolution, but on top of that limits the spatial resolution to never have cells larger than one of these lines. Is, for example, the red curve is 1 kiloparsec spatial refinement. So now we end up with a simulation that has 10 times the spatial resolution than the best simulations had before, and it has 1,000 times the number of resolution elements, because sadly the universe is 3D, so every time we gain a factor of 1,000 in mass, we gain only a factor of 10 in space. So this is now a good way in which we can keep the ISM treated in the same way, the galaxy treated in the same way, but we can increase the resolution in the CGM substantially in order to study the properties that the gas has in the halo. And that is what we've done. So here is what, I mean, obviously this looks much better when you just show it as an image. So now we have the gas density in a slice through the simulation, and you can see, all these individual colored blobs. Those are the individual cells, because we're using a moving mesh code called a repo. But you can see that usually these sort of higher density clouds are resolved with only a few of these resolution elements. So therefore probably not treated very well in their magnetohydrodynamic properties. So what our new method now does is, again, keep the ISM exactly the same, but add all this resolution into the halo. And if I flip back and forth, you can see that we go from something that looks quite poorly resolved and fuzzy in a way to much more structure. So, and just to say, this is about 80 times the number of resolution elements than we had before, but only cost 8 times the computational time. So it's a very efficient method, and this is the only reason we'd be able to do something like this. Otherwise, it would be prohibitively expensive if you just wanted to get to this resolution in a standard way. So what you can see in the differences, I'm going to go back and forth one more time, is that you get many more smaller, cold and dense gas clumps, and also the underdensities, which are these sort of darker red regions, are much more pronounced and better resolved. Shocks are better resolved also in this method. So here you have, you can see the same sort of variation, but it's it's not treated in a very accurate way, and we have all of this extra resolution, so we can now finally try to understand what sets the sort of gas structure and turbulence, for example, in this halo. So what does this mean for the galaxy now? So we have the galaxy treated in exactly the same way, but we added all this resolution to the CGM. Does that change how the galaxy accretes material from around it, or does it change how the outflows limit the amount of star formation? So these are 4 simulations. The blue one, again, is just this way we always did it, standard. Green is 2 kiloparsec refinement, red 1 kiloparsec refinement, and then the dotted black one is our highest resolution simulation. And that is the only one that shows a slightly elevated star formation rate at low redshift. So so this is look back time on the x-axis. So 0 is where we are now. And whether or not this is, so the first 3 resolution levels are exactly the same, statistically speaking. But whether or not there is a trend that with even higher resolution, you get enhanced star formation because you're now resolving higher densities in the CGM, which means that the gas can cool more efficiently and reach the galaxy more efficiently. That is to be determined, because if we have one simulation that's an outlier, we don't really quite have a trend yet. So we will see when we reach higher levels of resolution whether this trend continues. But in a way, it is it's good that it's not changing massively, because that would mean that all of our normal resolution simulations would not be converged in this sense. So it's in principle making a similar galaxy. And here I just show you the images of the stellar light in 3 colors. So on the left we have the lowest resolution in the CGM. So they're all the same resolution in the galaxy. On the left, the lowest CGM resolution, on the right, the highest. So you can see that the one with the highest resolution has a slightly bluer color because it has slightly enhanced star formation rate at low redshift. But the stellar mass of the galaxy changes by less than 0.1 dex. So it's in principle consistent with just being some random scatter in that happens because galaxy formation is a very stochastic process. And also the bulge to total or disk to total ratio is very similar in all 3 cases. So we're at least a little bit happy that we're not getting a completely different answer when it comes to the galaxy, so that we can still use our normal standard simulations as well. But now to turn to properties of the CGM itself. So here is, so I've projected the density into a 2D image by making column densities along 600 kiloparsec sidelines. And now you can see the 3 simulations. So this is just the hydrogen column density, but this is all of the hydrogen. So in principle, all of the gas, well, 75% of the gas. And you can see that these 3 simulations have very similar density profiles. So at least in the shaded region is the 1 sigma scatter around the median. And you can see that they're very much consistent with each other. But if we now, let me show you then what this looks like. So here on the left we have lowest, and on the right we have 1 kiloparsec resolution. And you can see that on average it looks pretty similar, but you get more structure when you have better resolution, which is understandable. But now if we look at something that's actually observable, so instead of all of the gas, we look at the neutral gas. So this is the neutral hydrogen column density. If you go from left to right, you can see that there is a clear increase in amount of neutral gas. So this is the gas that is about 10 to the 4 Kelvin. So for a CGM person, that's cold. For other people, that is very hot. So it is what I mean when I say cool clouds is about 10 to the 4 Kelvin. When compared to the hot gas that is at 10 to the 6, it is quite a lot cooler. So now let's quantify this, because we want to compare it to these observations. So here is a compilation of these quasar sightlines that probe the gas around galaxies. So on the x-axis, you see the distance from the galaxy that's observed. And then on the y-axis, you can see the neutral hydrogen density. And this is like 40 different galaxies. So it's, and also of 40 different masses at 40 different, slightly different redshifts, but approximately at a redshift of 0.2. So they cannot really be compared exactly However, it is the best that, that we can currently do. But what you can see is that there is a clear decreasing trend with radius, which makes sense because the density should decrease with radius, but the neutral gas should decrease even faster because it becomes, the gas is less and less likely to be cool enough to have neutral hydrogen as you go to lower and lower densities. So this is kind of the best sample that we have observationally for which we can compare our simulations to. So this is what one of our standard simulations looks like. And you can see that so I've reproduced these observational data points in black mostly, and you can see that there's a lot of, so again, we have the median of the neutral hydrogen column density and then the 1 sigma scatter around it. And you can see that there's a lot of data points that are quite far above what our simulations are predicting. And this is this is actually not just true for my simulations, it's true for simulations in general. And this is why people have written observational papers concluding that there's a crisis because our theoretical models cannot reproduce the amount of cool gas that is observed in the CGM, and therefore our understanding of galaxy formation is wrong. However, you probably expect this. When we add extra resolution into the CGM, we get this red curve, and we get a strong increase of neutral hydrogen column density by up to 1.6 dex, I believe, at about 50 kiloparsec radius. And now the 1 sigma scatter overlaps much better with the observations. But again, we have one galaxy that is about the size of the Milky Way, and the observations have a whole range of galaxies, most of which actually have lower masses. So take this all with a grain of salt, but at least it is interesting that you cannot just use these simulations to claim some underproduction crisis, because if you're not converging to the right, or if you're not converging yet, then you cannot quantitatively trust this this particular property of the gas. So here I've quantified it a bit better. So now I have the neutral hydrogen column density on the x-axis, and on the y-axis is the covering fraction of all the sight lines that are, or all the pixels in my case, that are above the value on the x-axis. So that's why so it's sort of a cumulative thing, but in the other direction. So this is how so you have many more sight lines that are low column density and many fewer that are high column density. And the black error bars are now those previous observational data points converted into a covering fraction, as I just explained. And again, our red simulation is this 1 kiloparsec refinement, and it goes right through the data. So I wrote this nice paper saying that we actually reproduce these observations, and there is no crazy problem in our understanding. It was always just a problem of resolution. Fascinating as that may be, I then ran a higher resolution simulation. So now I had 0.5 kiloparsec spatial resolution, and lo and behold, there is no sign of convergence yet, and the covering fraction and the neutral hydrogen column densities are even higher in this simulation, and this means that we're now overproducing the amount of cool gas in the CGM, which again, you cannot really compare these observations to this one simulation, but at least it's interesting that I'm now having the opposite problem of what people have always been claiming. And so I think this is definitely something, so it's not the final answer, but it's something that's very important to be aware of before you start claiming that your theoretical models are false, and that you need a different type of feedback or a different type of whatever in order to reproduce observations, because it might just be a resolution issue. It's not all terrible. So I've told you that the gas density on average is very similar. It's just the neutral gas that's different. Now I'm going to show you the radial velocity. So this is just a probability density function of all the gas in the inner CGM, so at a radius of 50 to 100 kiloparsec away from the central galaxy. And on the left, the negative numbers are inflow, and on the right, the positive numbers are outflow. And it's approximately a Gaussian distribution around 0. There's a little bit more inflow than there is outflow in these halos, which means that the galaxy is growing, which makes sense for something like the Milky Way, which is still accreting gas and still forming stars. And now if we look at the gas that we can actually observe in as neutral gas, this is actually preferentially inflowing very strongly. There's only a very small fraction of the neutral gas that is outflowing. But what I want to draw your attention to is that the fact that these distributions look the same in all of our simulations, even though they vary by, a factor of 10 in spatial resolution, or a factor of 1,000 in mass resolution at some points. So therefore, even though we have yet to come to a conclusion about the amount of this gas that there is in the CGM, it seems this is quite indicative that at least the properties of this gas are robust to changes in resolution, and that most of the H1 that we're seeing in the universe is part of an inflow, which is something that you cannot directly tell from most of these types of observations. So I wanted to leave resolution for what it is and ask the almighty question, but what about magnetic fields? So all of our simulations were MHD simulations. So they all had magnetic fields included, and they were following the MHD equations. But nobody checked to see what actually, so at some point, we wanted to study magnetic fields because they're an interesting topic, and we added this. Not me personally, but a member of my group added this to a repo, and then from then on they were all MHD simulations. But nobody checked to see what the actual effect on the CGM is, and that's what I'm going to talk about now in my final 5 minutes. This is again, sliced through the simulation that has 1 kiloparsec resolution. On the left, you can see the gas density, and on the right, there is the gas temperature. And for simplicity, I switched off AGN feedback. So in this simulation, there's only stellar feedback. But the conclusions are unchanged. It's just that the amount of cool gas and the amount of accretion will be higher in a simulation that has less feedback. Good. So you can see that I've rotated the galaxy to be edge on, so that outflows are happening mostly in the polar direction. So that would be in, up and down from the central disk. And you can also see that in the density and the temperature, because the density is on average a little bit lower there, and the temperature is a little bit higher there. So you get this bipolar outflow. And now, so this is without magnetic field. So this is different from the simulations I was showing you before. And this is the simulation with magnetic field. So the only thing that I've done is then have a seed field of 10 to the minus 10 Gauss initially at a redshift of 127 rather than 0. They follow the exact same equations other than that. I'm gonna flip back and forth a little bit so you can appreciate some of the differences. So you still get bipolar outflows, but the outflow may be slightly less strong and reach slightly less far. And definitely the structure of the cool gas is different. And also the region around the galaxy itself is quite different in the center. So let me show you then what the magnetic field looks like. So that is here in the top panel. You can see the magnetic field strength. So you can see that it's mostly a bipolar structure there as well. And that is because the turbulent dynamo is strongest inside the galaxy. So that's where you get the strongest magnetic fields. And then these are pushed out by, or dragged with the outflows that are coming from the galaxy. And that's why you get the highest magnetic field strength in these directions. And then on the bottom panel, I've now divided the thermal pressure by the magnetic pressure. So common wisdom is that this should be about a factor of 10. So 10 is normal. You would have 10 times more thermal pressure than magnetic pressure. And I don't disagree with that. That is absolutely the case when you average over the entire halo. However, if you look at like locally in these very, in these specific directions where the magnetic field strength is very strong, then it can actually dominate over the thermal pressure by 1 or 2 orders of magnitude. And therefore, it can be quite important for setting the properties of this gas. Let me first show you what it does for the gas and the metals, where these now move, where these move to. So I've told you that the gas accretes and from the CGM, but also gets ejected from the galaxy and perhaps from the halo if the outflow is very strong. And that is what you see here. So it's a cumulative gas mass profile, and in the solid curve, that is the one with magnetic fields, and the dash curve is without magnetic fields. Should have made a legend, but I forgot clearly. So without magnetic fields, you actually have much less gas, especially in the inner CGM, and also fewer metals in the inner CGM. And these profiles actually keep getting closer and closer together as you go to higher and larger and larger radius, and eventually lie on top of each other when they get to about a megaparsec. And so this means that without magnetic fields, you move the gas to much larger distances in these outflows, and the outflows are much more efficient than they are with magnetic fields. So magnetic fields sort of limit the flow of gas in such a way that it keeps more mass and metals inside the halo itself. And you can, well, no, I think that's just the point that I wanted to make with this. It also affects how the metals are actually distributed. So you have more metals in the CGM, but the distribution looks quite different, because here on the left, you have no magnetic fields, and you can see that in the direction of the disk away from the poles, you get still quite high metallicity, whereas with the magnetic fields, the metals all stay confined in this outflow region and don't really mix with the rest of the CGM. So you get a very different metal distribution, and metals are hugely important because they are responsible for most of the cooling of the gas in the CGM, and therefore allow accretion onto the galaxy much more, with high metallicity, you're much more likely to accrete onto the galaxy. So then to quantify this, you get, I think this is my last plot, you get that this is now the radial velocity on top and the metallicity on the bottom as a function of radius. And the simulation with magnetic fields is solid, without magnetic field is dashed, and you can see that the radial velocity is much higher, so less inflowing, more towards outflowing with magnetic fields, and much lower, so much more strongly inflowing without magnetic fields. So the inflows are also affected, and they're much more, so the outflows are, without magnetic fields, the outflows are more likely to escape, and the inflows are more likely to reach the central galaxy. Whereas with magnetic fields, everything is just a little bit more confined. And you can see this also in this metallicity profile, where you get a very strong relation with radius when you have magnetic fields included, and much more mixing when you don't. And that brings me to my conclusions. So I talked both about resolution differences and told you that it does not strongly affect the central galaxy or the average density in the CGM, but does affect the cool gas in the halo, and therefore changes the observed properties, because we can actually observe the neutral hydrogen and brings them more in line with observations. And then I've told you about magnetic fields, how they alter the flow of gas in the CGM, and they increase the amount of gas that remains in the halo and decreases the level of metal mixing. So then my final conclusion is that we can use observations to test our theoretical models, but it's important that you understand whether or not your particular property that you're interested in is converged in these simulations, and it is important that you include all the necessary physics.
Thank you very much, Freeke. Okay, I will ask if people have any questions. You can raise your hand, or you can just speak up, I suppose. So Will has already raised his hand. Will, why don't you go ahead? Oh,
okay, thank you very much. So it was a very interesting talk. I have a couple of questions about the physics ingredients you have. So first one was about the stellar feedback. So the question is, do you just include supernovae there, or are you including ionizing radiation feedback? And how does that affect the neutral hydrogen? And the second question was about the MHD. I was wondering whether you can rule out non-ideal MHD effects. Is it possible that non-ideal MHD might be important?
Okay, first question is so our stellar feedback is very basic and very terrible. So it does include more than just the supernovae, because we put in more energy than would be available from just supernovae, but we don't do it at all in a sophisticated way. So we just implement it kinetically. So and it's matched to produce a realistic size of mass, realistic stellar mass at low redshift, where we know we want to match observations. And that is really it. So it's definitely more than just supernova feedback, but it's not, so we don't have individual stars, because we just have stellar particles that represent the whole single stellar population. However, when we talk about radiation, there is a UV background implemented. So this is sort of the photons floating around in space from all galaxies that have produced it, and that is included. So there is ionization through that, but not through local sources.
Okay.
However, in the CGM, it's likely that UV that dominates. Then your second question, non-ideal MHD, I don't know. So this is all ideal MHD, and this is sort of, this is something that we've only been able to do recently. So there's a push towards also including non-ideal MHD effects and seeing whether or not they are important. But I think we're only now realizing, so I think we're only, so they're definitely important in some aspects of astronomy. And that's where the push is mostly, because I think in galaxy formation, we always sort of thought of them more as a diagnostic tool rather than dynamically important. So I'm hoping that, well, I'm not saying that this model is like the final, this one is correct. This one may also very well not be correct, and it may be important to include non-ideal MHD, but at least it shows that it could have a dynamical effect in some regions.
Okay, thank you very much. Bye.
Can't hear you, Sundar. Are you talking?
Sorry, forgot to unmute. Enrique has a question. Go ahead, Enrique.
Hi, thanks for the very interesting talk. We do similar things at much smaller scales, at the scale of molecular clouds. And so for us, it is very important to know what the magnetic field looks like and the environment around the molecular clouds. So have you ever looked at what the magnetic field looks like in your galaxies? What are the main features, the main topology or orientation of the magnetic field? How does it act in the spiral arms, etc.? What can you tell about the magnetic field in the galaxies that you form?
certain that someone has looked at it, but it has not been me. I have looked at the topology in the CGM, where you can see that where you have strong outflows and therefore a strong gas flow, they get aligned because they all move in the same direction. Whereas in the rest of the CGM, it's more turbulent, and you can see it's I don't know at the end of. So these simulations don't form super beautiful spiral arms anyway. They're still a little bit poor, but you can here you can see that there's a little bit of that, and can at least have an idea of. Oh, sorry, I wanted to pause it, not go away from it. What it looks like. I'm sure someone has looked at it, but I'm not. I don't know. In what sense this has been quantified.
So here the striations are. So what are we looking at here? Is this the magnetic field in the galaxy?
Yeah, so it's the magnetic field strength in the color, and then in the lines, it's some fancy way of making the. Well, it's of course in projection, but they're moving. They're in the direction of the magnetic field.
Okay, thank you. Very nice.
Thank you, Enrique. Jesus had a question.
Hi. I found it very interesting when you compare two models, the with and without the magnetic field. And in the case with the magnetic field in the edge on galaxy, you have these two bipolar flows that have been detected in X-rays in our galaxy, for example. Have you done any synthetic X-ray observations of this? Because this you can corroborate. If it's the magnetic field producing this, or I remember some people saying that it's supernova feedback, for example, instead of the magnetic field. So this can be something that can be tested by these simulations.
So you get bipolar outflows in both cases, and probably the ones that you see in observations are the ones that are closer to the center of the galaxy, right?
Yeah.
So I have not tried making synthetic observations. It's quite possible that they would look very different, but it's also quite possible that they would actually look fairly similar. It's hard for me to say because they're both, so they're definitely driven by feedback in our case. If we didn't have feedback, we wouldn't get outflows, right? We wouldn't even have magnetic fields out in the CGM really, because there's nothing to really bring it out and really get the halo dynamo going, because it's really the galaxy that is winding up the magnetic fields. So I don't. Yeah, I mean, so in our case, it's definitely feedback. That doesn't mean that's the case in reality, and I don't know how well you could be able to tell the difference, because you also have to realize that there's a lot of stochasticity in outflows, right? Sometimes you have a burst and sometimes you don't. Sometimes you have a burst, but it somehow collides with something and doesn't effectively get out. So you would want to kind of build up a statistical sample. And I don't know how difficult that is observationally, because this is kind of low mass for X-rays, right? Because most X-rays are around more massive galaxies than the Milky Way.
Yeah, but I mean, the observations are there. So you see these two bipolar things, and they're very confined. In your simulations, in the case
you
with
mean the Fermi bubble? Do you mean the Fermi bubbles?
Yes.
Okay. Well, that is on smaller scales than this, right? I don't think we have the. I don't think our feedback is, like small scale enough that we could reproduce that kind of structure. But you would get magnetic draping in one case and not in the other. So it is possible that even if you can't get it on that exact scale, that you could sort of make an analog at a larger scale. Like this is, these bubbles are like 50 kiloparsec or something. And that might still be interesting, but I haven't tried. I haven't even thought of that.
Okay, thanks.
Thanks, Jesus. Are there any other questions? Anyone else? I do have a question. So in one of the earlier slides where you were you were showing us the effect of different resolutions. You had one that was showing the galaxy morphology, and you had where the highest resolution had, yeah, that one there. So I missed it. You probably explained this, but so in the 0.5 kiloparsec case, you are getting many more stars. So you did mention this is stochasticity, but I didn't understand whether you were saying that either that because star formation is stochastic that you're catching more of it, or whether you're saying that your models, or whether you're saying this might be an issue with the models, that because it's so stochastic, you're just that this effect that you're seeing is not real. Which one was it? Sorry.
So I have an opinion, but I cannot prove it. So I think that so indeed there's more star formation at late times with this higher resolution, and you can see it in the star formation history quite clearly. So it's really at least it seems enhanced by a factor of 2 for a few gigayears, and I think this is robust. But I only have one galaxy, and people have also done studies about like the butterfly effect in cosmological simulations, and found that like even if you just make a tiny you choose a different random number, you get an effect that is, I think for stellar mass, can be easily 0.05 dex or something. So I cannot, based on one galaxy and based on only having one outlier, claim this, but I think it is. I think it is. It makes sense to me, because as you go to higher resolution, you're really getting more cooling in the gas that wants to accrete onto the galaxy. So it would make sense to me that it would increase the accretion rate. But I would need a better statistical sample before I can actually make these kinds of claims. So don't quote me.
So we have 2 follow-up questions. Bernardo has raised his hand, and then Enrique. So Bernardo, go ahead first.
Hi, it's regarding the same issue with the star formation. In this case, where you see an increase on the star formation, do you see also a different distribution where it happens? Do you see if it's more concentrated or in the outskirts of the galaxies?
I mean, I'm just looking at the figure now. I think it is really reasonably in the outskirts, but it's a little hard to tell. So I haven't looked at it, but from this image on the right, it does look like a lot of the blue light is coming from the outskirts.
In case, the strong bar must be affecting strongly where the star formation happens, no? Because you have very, very prominent bar.
Yes.
The structure of the bar, or at least it seems now that it's more elevated and longer in the higher resolution.
Yes. Again, there's definitely, it's definitely possible. However, it's also something that happens that is kind of that isn't necessarily robust. When you rerun your simulation with a different seed, you might end up with with either no bar or a different type of bar. I have some boxy peanuts here that disappear and appear and stuff. So I also don't think that this would be the most robust for an individual galaxy. Of course, if you give me all the computational time in the world, on a supercomputer, then I can just make a nice suite, and then we would be able to answer this question. But it's definitely possible that there is something about how, if the accretion is stronger, that you can also see the bar more. But like the actual gas in these central panels, they should be unaffected, right? So it should really then be, if it changes, it wouldn't be because of the anything in the ISM. It would really be because of changes in the CGM, because the ISM is left completely as it was.
I see. Thanks.
Thanks, Bernardo. So Enrique and then Will.
Yeah, so me again. I just wanted to ask you if you could show again the image of the magnetic field in the galaxy, and in particular, I wanted to catch the reference.
You mean the
2017 reference to that?
Oh, you mean the movie?
No, this Granted All. Okay. Yeah.
Oh, sorry, that's right too.
Yeah. So this paper, Granted All, does it have the images of the?
Sorry,
of the magnetic field?
Granted All. So the person who worked most on the magnetic fields is Pakmore, Akemor.
Okay.
So, and I know that he has some papers on the magnetic field inside galaxies.
Okay.
I don't remember exactly what year that is, but probably also around. So this is the suite of simulations was published in 2017. So the Pakmore reference must be 17 or 18.
Perfect. Okay, great. Thank you.
Thanks, Enrique. And Will?
Yes. Okay. So thank you, me again. Could you go back to the graph that you showed of the star formation history with the different resolutions? So this makes me doubt everything I've ever believed about numerical simulations, because you have there an apparent convergence. If you look at the first three simulations, they seem to be converging. And it's not just, often people would just present two simulations with a factor of 2 difference in resolution and say, oh, look, it's converged. But here you have 3 that have apparently converged, and then you make a further refinement, and then suddenly it hasn't converged. This is rather worrying, isn't it?
Yes. So it's not a resolution test in the standard sense of the word, right? So if you if you look here, then you can see that let's look at the blue and the green curve, that they are identical out to 50 kiloparsec. So even though I'm going to a higher spatial resolution, the mass resolution is actually the more important thing in the central 50 kiloparsec, and therefore doesn't change for most of the gas. Whereas normally when people show a resolution test, they increase the resolution everywhere. So then you can compare these things more more directly. And then also the star formation rate necessarily happens in the center, right? And the center is most likely affected by the stuff that is nearby the center. So then it makes the biggest difference if you actually increase the resolution, in the central 20-30 kiloparsec, which is only happening in this in the highest resolution curve. So it's not quite fair in that sense, because it's like 2 different resolution criteria, and I'm only varying one of them.
Okay.
So all the dense gas is treated in the same way as before anyway. So it's maybe as we go to this 500 parsec resolution, that's when enough of the dense gas gets affected, and it's the dense gas that is likely to accrete onto the galaxy. So that is the gas that is likely to enhance the star formation. That's my personal opinion. I think it's just at the 1 kiloparsec, I'm mostly refining the hot diffuse gas, which is, I think interesting and important, but I think it's less likely to affect the galaxy. Whereas if I go to the highest resolution level, that's when I also start affecting the and better resolving the cool clouds themselves.
Okay. I still think there's a moral there for us all, that we should never really entirely trust anyone who says that their simulation has converged. Absolutely,
but we should do what we can, I guess. But resolution tests are difficult. They're not clean, right? And including this galaxy stochasticity, it's always a little iffy. But
and so one final query: have you thought about including some sort of subgrid models for things like cloud destruction?
For things like
cloud destruction, like fragmentation of clouds. Like, would that be possible?
To have this type of physics in,
so turn it into some sort of recipe.
So I am not going that direction, but other people are. That's kind of the answer. So I think that, so there's a reason, there's a particular scale that would be nice to reach. So it's called the cooling length. It is, the time. It's whether or not when a gas cloud cools, it can adjust its density and stay in pressure equilibrium, or cool isochorically, and then its temperature drops, but the density basically stays the same. And that length scale is about 100 parsec depending on properties. Sometimes it's 10, sometimes it's a kiloparsec. but it's about this 100 parsec limit that I want to reach. I'm at 500 parsec now, and I think with more computational time and going to a smaller galaxy, so that can gain another factor 10 or 100 there, I can actually get there and do it properly. But I think other people are thinking of subgrid cloud construction. I'm just worried that you will then lose the sort of ability to actually try to resolve the CGM. Just like the ISM now is treated really terribly because we have all these subgrid models. So there's just certain questions we cannot answer with it because it is put in by hand. I am worried that if you start putting subgrid in the CGM, you will be in the same situation where you don't know whether your answer is coming from your model decisions. So I'm hopeful to be able to push to the necessary 100 parsec resolution in the future.
Yes, I mean, if you can do it all explicitly, then yeah, that would be great. Okay, thank you.
Only in certain cases. But you know, as computational power grows, hopefully everywhere. Yeah.
Okay, thanks.
Thanks again, Will. Maybe one more question, if anyone has anything to say. If not, then let's thank our speakers. Thanks, Freeke.
Thank you. This was wonderful.
Yes.